Hey students, welcome to lecture number 6 of Linear Algebra 2. So today we want to talk about determinants again. So determinants were defined for square matrices A, an n by n matrix like this with entries A, I, J. And then the determinant was defined by this formula here. And last time we proved that a matrix A is invertible if and only if the determinant of this matrix is non-zero. And also last time we mentioned this theorem for 12 here, stating that if we take two determinants A and B, then the determinant of the product of these two matrices is the product of their determinants. But this theorem we didn't prove yet, and the goal of today is to prove this theorem here. Okay, but first let's recall a little bit from last time. So last time we also talked about these row operations which we saw in Linear Algebra 1. So there were basically three types. So if I have an n by n matrix and I take some I, j smaller than n, which are different, and I also have some number lambda, then row operation R1 was to add j lambda times the jth row to the ith row. R2 was to multiply the ith row with this number lambda, which is non-zero. And row operation R3 was to just change the jth row with the ith row. And then we saw that if we do this to a matrix A, for example, if we apply the row operation 1 to A and call this new matrix B, then we don't change the determinant. In the case using R2, so multiplying a row with the number lambda, then we see that the determinant changed by just also multiplying by this lambda. And swapping two rows meant that the determinant changes its sign. And these row operations we now want to describe by using matrices. So instead of doing these row operations, we will multiply with certain matrices which are called elementary matrices. So there are three types for each row operation. So again, lambda is a non-zero real number, I and j are smaller than n. And then we define three types of n by n matrices. So the first one is denoted by r lambda j I. So this is this matrix here, which is basically the identity matrix, meaning we have ones on the diagonal and zeros everywhere except for this place here. So this is in the j's column, and in the ith row there we have this number lambda. Then the second matrix, this r lambda I, is basically just the identity matrix, but here on the diagonal at rows I and column I and rows I, we put a lambda there on the diagonal. And the last matrix is Rij, which is again basically the identity matrix, except that here in the ith row I have a 0 on the diagonal, but then I have a 1 on the j's column, and here in the j's row I have a 1 on the ith column. And the rest, everything I didn't write down here, is 0. Okay, so let's do one example. So for example, in the case n equals 3, and let's say lambda is, what did I choose here? No, maybe for arbitrary lambda. So maybe let's put this here to see these matrices. So what is, for example, r lambda I 1, 3? So this means that here in the first column we have a lambda in the third row. So there's a lambda there. And the rest is just the identity matrix, meaning here we have ones on the diagonal, and the rest is just 0. And what is an example for the second one here? So for example, r lambda 2 means we have the identity matrix, but here at this position we have lambda. And an example for this one, for example R1, 2, means, well, here we have this 1, but here we change these positions like this. Okay. And so first, simple properties of these matrices. So maybe let's put this down here. So first, what are their determinants? So what is the determinant of R lambda J I? Well, if you would calculate the determinant of this matrix, then there's again just one pattern which gives non-zero contributions, which is just the entries on the diagonal. So this determinant is just 1. Then the determinant of R lambda I, with the same argument, the determinant of this diagonal matrix is just the product of the elements on the diagonal. So in this case, this is just 1 times 1 times 1, and at some point we multiply with lambda, so the determinant is lambda. And here, in this Rij, oops, not this, but the determinant of this, Ij, well, there's also just one pattern which gives a non-zero contribution, but this sigma corresponding to this pattern has exactly one inversion given by this thing here, and therefore we will see that, or we see that the determinant of this is -1. And then the properties, so these are the determinants, and you see that all of them are non-zero. So this lambda is non-zero, so also this is non-zero, and therefore these matrices are also invertible. So what is, for example, the inverse of this matrix here? Well, you can check that if you, instead of taking lambda Ji, if you take minus lambda Ji, then this will be the inverse of this. So for example here in this example, if you consider minus lambda 1, 3, so this is this matrix. If you would multiply these two matrices, then you will see that, oh, of course, here I need to put a minus lambda here, that R lambda 1, 3 times R minus lambda 1, 3, that this will give exactly the identity matrix. And here, for this position here, what we would multiply is this vector with this vector. So we get the minus lambda plus 1 times lambda, and therefore we have this 0 here. And we see that this is this inverse of this matrix here. And similar here, the inverse of this matrix, well, what matrix do I multiply with this to get the identity matrix? And you see that if I, instead of taking lambda on the diagonal, I take 1 over lambda, then this gives the identity matrix. So this is 1 over lambda I. And also here, the determinant, not the determinant, the inverse of this matrix, Rij, is just the matrix itself. So if you multiply this with itself, then you get the identity matrix. Okay, so in particular all these matrices are invertible because the determinants are not 0, and their inverse are also given by elementary matrices. Okay, and now we want to show that multiplying with these elementary matrices corresponds to applying these row operations R1 to R3. And this is the statement of this proposition. So the first one is, if I have a matrix A, an n by n matrix, and I multiply it with this matrix, the first one of these elementary matrices, R lambda Ji, then this new matrix is a matrix I get from A by applying this row operations R1 which meant that I add lambda times the jth row to the ith row. And the second statement is if I apply the second elementary matrix R lambda I to A, what I get is the matrix which comes from using this row operation R2, which just meant multiplying the ith row with lambda. And here's a typo, so there shouldn't be a lambda. And the third statement is that this Rij, if I multiply it with A, then this swaps the j's and ith row, which is our row operation R3. So let's prove this. I will just do number 1, and the 2 and 3 you can try to do by yourself. So first, this R lambda ji, so this was this matrix here with 1 on the diagonal, and at some point I have this lambda at the jth row and ith column. So this is the same as taking the identity matrix plus lambda times the matrix, which is 0 everywhere except at this position where I have this lambda here. And this matrix we want to call Eij. So if this has entries small eij, then these eij's are 1 if, oh, maybe let's give them other names. So let's say KL. So this the entry at the position in the k's column and lth row is 1 if this j is L and the I is K, meaning we have this 1 here, and 0 otherwise. So therefore this matrix here, so if I multiply this matrix with A, this is the same as multiplying with the identity matrix plus lambda times Eij. So in other words, this is A plus lambda times Eij multiplied with A. And now what we want to show is that this matrix here, so if I multiply the matrix Eij with A, what I get is just the j's row of A, but now in the ith row. Because then this identity would mean that I take A plus lambda times, and then I take at the ith row, I have the entries of the j's row of A. So let's see why this is the case. So if we multiply this with A, this means we have this matrix with a 0 everywhere, except there's a 1 here at column J and row I. And let's say A has entries Aij, so I multiply here with A11, A1n, AN1, ANN. So and if I multiply this, so what matrix do I get? Well, here in the first, so here I have zeros everywhere. So the first I minus 1 rows are just 0. But then at this row here, I get some entry here. So in the ith row, what do I get as entries? So if I multiply this vector here, then because here I have the jth row, I take the jth entry here. So the first entry here would be aj1, the second entry would be aj2, up to ajn. So this is really the j's row here in A, but now it's in the ith row. And this shows that this matrix here is exactly the matrix A plus lambda times the j's row added to the ith row. And this is exactly what we wanted to show, that multiplying with this matrix here correspond to adding j times the jth row to the ith row of A. And 2 and 3 are with a similar but maybe even easier argument. So if you just see what happens if you multiply this matrix with A, so if you would take the identity matrix but at some point you have a lambda, then you get exactly the matrix A, but the ith row gets multiplied by lambda. And here you can also see that with a similar argument that the jth row gets swapped to the ith row and the ith row gets swapped to the jth row. Okay, so this is this proposition here. So now instead of saying we use the row operation, we can also say that we multiply with these elementary matrices. And one consequence of this is this corollary. So the first statement is if a matrix A is invertible, this is the case if and only if it's a product of elementary matrices. And then the second statement is if C is an elementary matrix, so one of these three matrices, then the determinant of C times A is the product of the determinant of C times the determinant of A. So somehow this is a special case of this theorem we want to prove in general after this. But now the statement here is just for the case when this matrix C is an elementary matrix. But first, let's see why number 1 is true. So here we have an if and only if. So we want to show if A is invertible, then it's a product of elementary matrices, and if it's a product of elementary matrices, we want to show that it's invertible. So let's do this direction. So if A is invertible, well, this means that we can use these row operations to get the row reduced echelon of A, a row reduced echelon form of A. And if A is invertible, this is always the identity matrix. But now we have this proposition saying that doing row operations corresponds to multiplying with elementary matrices, and therefore going from A to this identity matrix just means we need to multiply with elementary matrices, but this in other words just means that we can also write A as a product of elementary matrices times this identity matrix. Well, multiplying with the identity matrix doesn't change anything, so A is just the product of elementary matrices. Because we can go from the identity matrix to A by multiplying with elementary matrices. So this would do this row operations, but also the inverse is done by multiplying with elementary matrices. So these Ci's up to Cm's are elementary matrices. Let's say with but also this somehow shows the other direction, because if A is a product of elementary matrices, then we know that these elementary matrices are invertible, and so we can explicitly write down the inverse of A. So remember, if I take the inverse of a product of matrices, then I need to reverse the order. So this is the inverse of this product. And this is just Cm inverse times Cm minus 1 inverse, so up to C1 inverse. So in particular, A is also invertible because it's a product of invertible matrices. And for the second statement, this is basically just a reformulation of everything we saw before. So here, this is the second statement we want to show. If C is an elementary matrix, then we have this formula here. But what we saw last time is this proposition here, namely that if we do, for example, row operation 1, then the determinant doesn't change. And we just learned that doing row operation 1 means we multiply with this matrix here. and the determinant of this matrix is 1. And therefore we have exactly this statement here, because the determinant of this product means by this here that this is just row operation 1, but row operation 1 means the determinant doesn't change. So here on this side we still have the determinant A, but on the other side we also learned that the determinant of this matrix is 1, so here the determinant of A is just determinant of A. And with the same argument we see that here the determinant of this matrix is lambda, and therefore the product of this, the determinant of this product, is also given by multiplying with lambda, so this statement is also true. And similar here, because the determinant of this matrix is -1, then using this argument and this, we see that this statement also holds for this matrix. And here's again this stupid typo. Okay, so this is now, so we now have this corollary, and with this corollary we now want to prove our main goal of today, namely that this formula here holds for any matrix C and not just for elementary matrices. So this is now the proof of this theorem we mentioned at the beginning. So we want to show that for any AB this formula holds. And for this we will use this corollary we just proved. And now we will distinguish two cases. First case, A is invertible, and then the case when A is not invertible. So case 1, A is invertible. And then we see by this corollary, A can be written as a product of elementary matrices. And now we want to prove this statement here by induction on the number m here. So we want to show that for any matrix B, the determinant of the product A with B, where A is a product of m elementary matrices, is a product of this. So induction on m. So if m is 1, so this is the base case. So if A is just C1, then this formula here is exactly what we already did in the corollary, because the determinant of A times B is then just the determinant of C1 times B, but C is an elementary matrix, and therefore by this corollary this is the same as a determinant of C1 times determinant of B, and this is just the determinant of A, because A is just C1 in this case. So the base case m equals 1 is just given by this corollary. Oh yeah, I think we also called this the base step, because so now comes the induction step. So in this step we assume that if A is a product of, let's say, m-1 elementary matrices, then this formula here holds. So in other words, if I have that the determinant of, let's call them C2 up to Cm, so these are now m-1 elementary matrices times some matrix B. So we assume, we already know that then this can be written as the determinant of the of these times the determinant of B. So this is the induction hypothesis. So we assume that this is true. And now we want to see what happens if A is now this product C1 up to Cm. So let's see, so determinant of A times B is determinant of C1, C2 up to Cm, B. And now, so this here, C2 up to B, is some matrix multiplied with an elementary matrix. And we know that the determinant of some matrix with an elementary matrix, there we can take the product of these determinants. So here, this is again, let's do it orange for the, so this is again the corollary. So this is the determinant of C1 times the determinant of this matrix here. So it's just C2 up to Cm times B. But now we have the product of B with a product of m minus 1 elementary matrices, and for this we assume that our statement already holds, so this induction hypothesis. So we can, by using this, the induction hypothesis, rewrite this determinant here. So this determinant of C1 is just still there, so it's just still determinant C1. But now here we can write this as the determinant of C2 up to Cm times the determinant of B. But now here we have the determinant of one elementary matrix with this times the determinant of some matrix. And here we can use again the corollary. So we can again put this C1 in there. So this is again the corollary. So this is determinant of C1, C2 up to Cm times the determinant of B. But this one here is just A. So we see the determinant of A times B is the determinant of A times the determinant of B. And therefore this statement holds for M, assuming that this statement holds for m minus 1 products of elementary matrices. Yes, and this proves the case of this theorem if A is invertible. But now we also have the case 2. A is not invertible. Well, in this case we know from last time that then in this case the determinant of A is 0. So we know here in the formula the right hand side is 0, and now we just need to argue why then the determinant of A times B is also 0. And now, so A is a square matrix, and the statement that A is invertible in the case when A is a square matrix, we learned last semester, is the case when A has full rank, or in other words when the image of A is the whole Rn. So maybe here recall. A square matrix is invertible if the image of this matrix A, so the image of A were all possible vectors I can obtain if I multiply vectors with A. If I can get all of them, then this meant that the linear map attached to this matrix A is surjective. But in the case when it's an n by n matrix, then this multiplying with A is just a linear map from an n-dimensional vector space to an n-dimensional vector space. And in this case, being invertible, I mean this we did for general linear maps, being invertible in this case means we just need to check if it's surjective or injective. And if the image is the whole space, then this meant that A is surjective. So, but the image of this product of A times B, so the image is the set of vectors I can obtain by multiplying this matrix with some vector. But this, of course, is contained in the image of A. because if I multiply from the right here with a vector with this b, I get some vector, and then therefore in particular the image of the product here is contained in the image of just the matrix A. But in this case A is not invertible, and therefore the image of A is not the whole space. But this also means that the image of A times B is not the whole space, because this is contained in the image of A, and therefore A times B is not invertible. But if A times B is not invertible, then we know that the determinant is also 0, and therefore 0 is the same as determinant A times determinant B, because determinant A is already 0. No matter what B is, this will always be 0, and therefore this equals the determinant of A times B. And therefore the statement also holds when A is not invertible. Okay, so this is the main thing we wanted to prove today, but I want to mention one more thing. So if you want to calculate determinants, so we had this definition here, this formula given by the sum over all permutations of the set 1 to n, and then we need to take this product here. But there's also some inductive way to do this, which is called the Laplace expansion, and this I just want to mention, but I will not give a proof. But I think this is quite useful to know to calculate determinants. So we start with a matrix A, which is an n by n matrix, and now we fix an I and a j, and then what we want to define is the matrix Aij. So this is A, so this will be a smaller matrix. It will be an n minus 1 times n minus 1 matrix. And what we do is we remove the ith row and the jth column of A. Ith row and jth column. So for example, let's say I have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A, let's say 1, 2. So this means I remove the first row and the second column. So this gives now a 2 by 2 matrix, 4, 6, 7, 9. So just the remaining entries here. And then the statement of this Laplace expansion is the following. Oops. So then the statement is that the determinant of A, what I can do, so there are now two versions. I can expand among a column or among a row. Oops. And so, for example, I can expand along the ith row. So what I take is the determinant of AIL. So I fix now a row. For example, I could fix the first row, and then I go through all columns. So I can go 1, 2, 3 columns here, and then I take the determinant of the corresponding matrix, which I obtain by removing the ith row and the jth column. But I also have a factor here, which is minus 1 to the I plus L. So this would be an expansion along the ith row, but you can also take an expansion along the jth column. So again, you have the determinant of A. So now you fix the column and you go through all possible rows. And here the factor is minus 1 to the L plus J. So this factor here, it's quite easy to remember. So every time you consider the determinant of AIL, you take the factor minus 1 to the A plus L. So this means that in this matrix you could think of plugging some checkerboard style, some kind of a checkerboard with plus and minus. And for example, in this case here, A1, 2, I just need to look here, oh, this is a minus. So the contribution here would be minus 1 times the determinant of, oh, I also forgot to put here the A, I, L, and here also A, I, L, sorry. So in this case I need to multiply with minus 1 times 2 times the determinant of the remaining matrix. So let's do this example here. So we have this matrix A, which you already know from the homework. And so to use this Laplace expansion, you always need to look for columns or rows with a lot of zeros. So in this case, there are many possible choices. But for example, we could take the expansion along the first row. So let's take this one here. So in this case, the determinant of A is, so we need to think about the signs. So here it's a plus sign, minus, plus, minus. So it's a determinant, oh, sorry, so it's 1 times the determinant of the matrix I get by removing the first row and the first column. So it's this matrix here. So it's a determinant of 1, 0, 3, minus 1, 1, 0, 0, 0, 5. And then the second, so this doesn't give anything, so it would be minus 1 times, minus 0 times the determinant of this. But now it's plus minus 2, so plus minus 2 times the determinant I get by erasing this part here. So it's 0, 1, 3, 0, minus 1, 0, 3, 0, 5. So now we have the sum of two determinants of size 3. And now we can do it again. So here, to get this matrix, now, for example, we could expand along the last row here. So the signs are plus, minus, plus, minus, plus. So it's 5 times the determinant we get by removing this and this. So it's just the determinant of minus 1, 0, minus 1, 1, which has determinant 1. So this determinant is just 5. And then we have this matrix here, where we could, for example, take the expansion with respect to the first column. So the sign is plus, minus, plus. So it's plus 3 times the determinant of this matrix here. And the determinant of this thing here is, so it's 1 times 0, it's 0, minus, minus 1, 3. So it's minus 9, but here we have minus 2, so in total this is plus 2 times 9, so plus 18, minus, sorry, so this has the determinant plus 9, sorry, so this should be minus, so here the determinant, this is minus 3, plus 3, so it's 3 times 3 is 9, times minus 2, so it's minus 18, so this is minus 13. And the determinant of this matrix is minus 13. But of course you could also, instead of taking the first row, you could take the first column, or here the third row, and so on. And this is quite helpful tool, this Laplace expansion, to calculate matrices which have a lot of zeros, because then you can always choose a column or row with a lot of zeros and reduce it to a problem of calculating the determinant of smaller size. Okay, so that's all for determinants, and next time we will start with a new topic on eigenvalues and eigenvectors, where we also use these determinants, and there we can also see that we will have a lot of nice applications for this. See you then.